Right. Now let's discuss some more examples on antiderivatives. I'm doing the second worksheet. Sorry for that sound. I'm doing the question number 2 of the second worksheet. There are 3 parts. Let's try to come up with solutions for all the 3 parts. So the first part is we have to calculate the antiderivative of 15 times cos 3x. So what do we mean by an antiderivative? We have to find a function, certain function, so that when you differentiate that function, you should get the previous one. So we call this capital F as the antiderivative of simple f. Right? So what should be the function so that when you differentiate this function, you should get this as the answer. So what is the suitable function? Now to compute these antiderivatives, there are certain rules similar to the derivative rules, but here we are not using any of these. We are just thinking backwards from in our differentiation, right? We are going backwards through our differentiation techniques. So just by looking at this term, we should identify what is the suitable function that we have to write here. Now, a good place to start is from this cos x term. Now, in order to get cos x as the derivative of a certain thing, definitely you should have sin x as the base term, right? And since you have cos 3x here, it's reasonable to write sin 3x here as well. But then what will happen if we just leave out capital F like this? Now, when you differentiate capital F, if this is the correct antiderivative, when you differentiate this one, you should get the previous term or the previous function as the answer. But let's see what will happen when you differentiate this one. When you differentiate this term, you should use the chain rule. Then you will get cos 3x times 3. But that is not the original problem that they have given. Instead of 3, you have 15. So we can make a small change in our proposed capital F. What if we write 5 in front of sin 3x? Then you will get the same term as the derivative, but it will be multiplied by 5. So that then you will get 15 cosine 3x as the answer, which is our original function that they have given. In other words, when you differentiate capital Fx, you will get simple fx. That means capital F is the antiderivative of simple f. But there's another important thing that you should not miss, right? Now this is true, this is an antiderivative, but it is not the only antiderivative. Even if you write another additional constant term, you will still get the same result when you differentiate it, because when you differentiate a constant, you will get 0 as the answer. So still, even though you write it as this whole thing, when you differentiate it, you will get the same result as the answer. So in fact, the antiderivative of 15 cosine 3x is 5 times sin 3x plus c. Don't forget to write this arbitrary constant. Okay? And then we can move to the next question, which is x squared minus x divided by 3 minus 3x. Now in this function, at once if you start to think what should be the suitable function so that when it is differentiated, it should give this as the answer. If you start to think at once, it will be difficult because it is a fraction. This original term or the function is a fraction. So it will be very hard to imagine a suitable antiderivative. But you can do some further simplifications and then think about the antiderivative. Whenever it is possible to do some simplifications, some factorizations, you should have the habit of doing that first. Okay, right. So here we can factor out the numerator as x minus 1 over 3 1 minus x, right? So we can see that you can cancel these two terms, but you should get a negative sign in front. That means when you have x minus 1 divided by 1 minus x, you can write the numerator as it is, and the denominator you can take minus 1 out and write x minus 1. So when you cancel these two things, you have minus 1 remaining. So you can do that in this fraction. So you will get negative x over 3 as the answer. But be careful, here you can do that only when x is not equal to 1. Okay, because when x is equal to 1, this term will be 0 and this term will be 0. So we will end up with a 0 or 0 situation, which is not a possible, which does not have any suitable simplifications. So simply you can write this one as this when x is not equal to 1. Then once you obtain this simple, more simplified term, it's easy to figure out the suitable antiderivative, right? So what should be the capital Fx so that when you differentiate it, you will get this as the answer. Then it's simply x squared. When you differentiate x squared, you will get 2x. But that's not the exact thing that we need. What we need is, we should cancel out this 2. So I am writing 2 in the bottom. And you should get a minus sign. So I am writing a negative sign. Also, you should have an additional 3 in the bottom, right? Now see, if you differentiate this function, you will automatically get the previous original simple f as the answer. See, now all these things are constants, so you can take everything out. And when you differentiate this one, you will get 2x. And when you can cancel these two terms and you will end up with simple fx, right? And the other important part is, this is not the only possible value for an antiderivative. You can add another additional constant c. So altogether, this will form the antiderivative of this fraction. So this is still, we are still thinking reversely through our derivative rules. Okay. Now the last question of the second worksheet. Simple fx is given as 2x plus 5 whole thing to the power 7. So what should be the suitable antiderivative of this simple f? Now this capital F and simple f are just some random letters. Okay, you can use whatever the notation you prefer. Okay, there's no big importance of using f, the letter f, as these functions or the antiderivatives. That doesn't play a major role. Okay, so what should be the suitable term? Now we are doing it just some sort of with a trial and error method, but still we are applying our differentiation knowledge as well, right? So how about this? If you have this, when you differentiate that function, what you will get is we are applying this rule. When you have a function raised to a certain power, and when you differentiate it, you will get fx n times fx to the power n minus 1 times f prime x. So when you differentiate this one, you will get 8 2x plus 5 to the power 7. Now, our main goal should be to get this one in the suitable way. And it's okay to have some difference with a scalar multiplication, because you can easily counterbalance the errors. Okay, but first of all, we should target our antiderivative in a way that it gives the appropriate powers, and the rest you can simply adjust. Okay, right. Now we have the corresponding powers, and also this should be multiplied with 2 according to the chain rule of derivatives, right? So this is the derivative of our suggested capital F, but it is not the correct answer. You will have 16 times 2x plus 5 to the power 7. So what is missing here? Now, in the expected result, you should not get anything as a coefficient, but here you have 16 as a coefficient. So you can do a very minor adjustment. What you can do is, you can just write 16 here. Now, if we consider this as our original antiderivative, then you will be dividing everything by 16, and you have this as the answer, which is our expected result. In other way, if we propose capital F to be 1 over 16 2x plus 5 to the power 8, then when you differentiate this one, you can get simple fx as the answer, right? But here also you should not forget that we can add another arbitrary constant with each constant, and this is very, 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 very important. Okay, right? So if we have this relationship, we call capital F as the antiderivative of simple f.